In this video, I introduce a navigation world model. Navigation world model is a video generation model that predicts future vision observations based on past observations and navigation actions. Navigation world model captures environment latent dynamics using a conditional diffusion transform, which is trained on diverse video collection of demonstrations as shown here. This navigation world model. This past observations, these actions, and this mode output. Given a start image actions and a goal image, a goal condition, the world model aims to generate a path towards the goal. Navigation world model S for theta is a stochastic mapping from a latent state S tau and action A tau to future latent state S tau plus 1, where theta is the model parameters and the latent state S tau is generated by a trained variational autoencoder as shown here. Conditional diffusion transformer is used as a world model to simulate a stochastic environment as shown here as one block of the conditional diffusion transformer. This is the input, this condition action, and this is the context state as tau. This block includes three components. The first one is self-attention, which uses the goal state as the input, namely query key and value are calculated from the goal state. It's gamma and beta mean and variance of the feature distribution. Second component is cross attention, namely a Q from a target state, a key, and V from the context states here. Alpha is a noise schedule. The third one is a pointwise feed-forward network, as shown here. In the forward diffusion process, noise is added to the target state as a tau plus 1 according to a randomly chosen time step t. The noise state as tau plus 1t is defined as here, where noise E sampled from a normal distribution. AT is a noise schedule controlling variance. As t increases, as tau plus 1t converges to a pure noise distribution. The reverse denoising diffusion process recovers the original state as tau plus 1 from a noisy state as tau plus 1t condition on the previous state as tau. The current action A tau and the diffusion time step t. The denoising model is defined as f theta. The reverse denoising diffusion process is trained to minimize the error between the predicted and the target state through a denoising process, defined as here and shown in this figure. Where time step t is sampled randomly to ensure that the model learns to denoise frames across the various levels of corruption. By minimizing error, the denoising model learns to reconstruct as tau plus 1 from his noise as tau plus 1t condition of the state as tau and action A tau. A trained navigation world model can be applied to plan navigation trajectories for us. Familiar environment, navigation world model can simulate navigation trajectories and choose the trajectories that reach the goal. In an unknown environment, a long-term planning might be rely on imagination. Given the initial latent state S0 and target as a start, navigation world model looks for a sequence of actions from A0 to AT-1 that maximizes the likelihood of reaching the target state. S is a normalized score for reaching state as a star with ST given initial condition as 0, action A, and state S obtained by autogressive rolling out the navigation wall model. The energy function E is defined as a negative similarity score as shown here and explained in this figure. This similarity score as input actions A and initial state, this predicted state ST, and this target state from the target image. Where S star and ST are computed by using the pre-trained variation autoencoder decoder. The planning problem reduced to finding the actions that minimize the expected energy function as shown here. The cross-entropy method is applied to optimize the model predictive control problem. The pre-trained navigation wall model is applied to optimize the standalone plan goal conditioned navigation trajectories by finding a sequence of actions from A0 to AT-1, given a start state as tau and the goal state as star. Cross-entropy method iteratively updates the probability distribution of trajectories to improve likelihood of getting better solutions. The main steps of trajectory optimization process are summarized below. First, define a Gaussian distribution with mean mu and variance sigma over the solution space, and then generate n candidate solutions by sampling from the current Gaussian distribution. The solutions generated by navigation wall model is evaluated using LPIPS score between the predicted and the goal images. A set of better performing solutions are selected, and then the parameters of the distribution adjusted to increase the probability of generating solutions by minimizing the cross-entropy error between the old and updated distributions. Repeat the sampling, evaluation, selection, and update steps until a stopping criterion is met. For more details, please check with these references. Thank you. Bye.